let me quickly tell you what the plan is before we start. So we have only 5 lectures left now, right? You can see, right, the screen? Okay. So we have 5 lectures left. Today we want to try to finish chapter 6. Exactly. Yeah, so we want to finish chapter 6 today and start with 7a until a certain point. And then in the next lecture, we'll try to finish 7a. Okay, so that is sort of the point. And if you're not able to keep up, what do you guys prefer? Do you prefer that we have some? Did I mess up something? What are you laughing at? Okay. I thought I messed up something on the note. Okay. If I do not manage to finish, do you prefer that I give you supplementary recordings for each lecture the same day? Or do you prefer that we finish the 4 lectures and then I give you whatever we couldn't finish later? What do you guys prefer? Same day is better? Show of hands for same day? Okay. So I'll give you on the same day. Okay, so if you're not able to manage until whatever the statement 7.10 is, I will give you until then as a recording. Okay? Reasonable? So let's start. Yeah, this is because we have to synchronize with everyone, right? So we're a little bit behind this time, unlike the last time, which is good, which means people are following. All right. So last time we looked at the Gram-Schmidt procedure, right? So Gram-Schmidt was basically saying what it was saying: if I give you a bunch of linearly independent vectors, you can construct an orthonormal basis out of it, or orthonormal. Okay, this is what it says. Okay. Okay. So now we're going to look at the following. So we are going to say that so we recall the definition of an upper triangular matrix. So what is an upper triangular matrix? We know this very well. So if you have a matrix, it basically has non-zero entries here, and these entries are zeros. That's fine. Okay. All right. Now, in the last chapter, we showed that if V is finite dimensional, if V is finite dimensional and complex, right? This is just a recall, okay? So this we already did. So if V is finite dimensional and complex, then for each operator on V, there exists a basis such that matrix, or say the operator was, let's call it T. So the matrix of T is upper triangular. You remember this? Yeah. Okay. So, but now we are dealing with, inner product spaces. Okay. And so therefore we want to know whether there exists. So does there exist an orthonormal basis for which this is the case? There exists. Does there exist an orthonormal basis with the same property? Is the motivation clear? What we're trying to do? Okay, so earlier we said we could make everything into upper triangular. Now we're asking, can we do it in particular using orthonormal basis, not just any basis? Okay, all right. So the next result is basically going to show that the existence of a basis with respect to which T has an upper triangular matrix implies the existence of an orthonormal basis with the same property. Okay, so what is it saying? So we'll write down the theorem statement more carefully. So it's basically saying if there exists a basis with respect to which T is upper triangular, then there exists orthonormal basis as well with the same property. Okay, is that clear? So that is the starting point, and then combined with the previous result, we'll get the statement that for every matrix T, one can find an orthonormal basis in which it would have this upper triangular form. Is that okay? Is the overall argument fine? Okay, very good. So let's state a lemma. So we'll state it as a lemma because we use it for a different proof. So the statement is formally, suppose T is a linear operator on the vector space V, if T has an upper triangular matrix, it's basically the same statement that I wrote, but I'm writing it again just to make sure we know what the formal statement is. This is 6.37 now. Has an upper triangular matrix with respect to some basis of V, then T has an upper triangular matrix with respect to an orthonormal basis. Triangular matrix with respect to an orthonormal basis. Right? So this is the statement. We're going to push the proof. I'll send you a proof as a recording. Okay, the idea is very, very simple. It is basically just using the fact that when you do Gram-Schmidt, it's using two things. Okay, first is it's using the fact that there was this proposition. I'll remind you what the proposition was. The proposition. Okay, so now I'm telling you the proof idea. Okay, so the proof idea uses two things. So one, it uses this proposition. This proposition basically says that if you have a matrix T that is upper triangular, okay, then the following things are equivalent. Okay, so the first is obviously that it's upper triangular. The second is that there are properties about the span. Okay, so in particular, we have that the operator acting on Vj keeps you inside the span of V1 to Vj. Okay, this is something we already proved. And you can check that in the Gram-Schmidt procedure, all the basis vectors you're creating are basically inside the span of the previous ones anyway. Okay, so that is the high level idea. Okay, you can check the proof. I'll also send you a recording later, but that is the key idea. Okay, making sense? M, is it making sense? Are you lost? If you're lost, tell me. Where did you get lost? So the statement was the statement clear? No. Okay. So the statement was the following. We were saying, what did we want to know? So we know that for an arbitrary matrix, right, in the complex field, you can always find a basis such that the matrix has upper triangular form. This we proved in the previous chapter. Okay, what is the new thing we learned now? We learned something about orthonormal basics, right? We learned Gram-Schmidt and we saw that you can make an orthonormal. So the natural question is, can you also make the same statement, but with respect to an orthonormal basis? Earlier we said there is some basis. Now we're saying, can it be an orthonormal basis with the same upper triangular property, right? And it turns out you can. So the statement is, if T has an upper triangular matrix in some basis, one can convert it into upper triangular in the orthonormal basis. Okay, that is the statement. And I was just saying, this is what is the proof idea. I'll give you a recording for the proof, for the full proof later. The proof idea is very simple. It just uses two facts. One, it uses this equivalence. So we showed in the previous lectures that a matrix T being upper triangular is equivalent to checking that when the operator T acts on Vj, okay, that vector stays inside the span of V1 to Vj, where V is the basis in which it's upper triangular, right? So that's one property. The second property is that, remember, the Gram-Schmidt procedure is basically just creating linear combinations of vectors from V1 to Vj anyway. Okay, so you basically have to combine these two ideas. And it is not that difficult to check that even the orthonormal basis will satisfy this property. I'm sorry for that. Is that okay? Yeah. Okay. All right. So let's continue. B, is it okay? C, all good? Shall we move on? Okay. All right. Okay. So now the next result is a very important application of this previous result, which is called Schur's theorem. So Schur was a German mathematician who first published this result in 1909. Because it's a very old result. And because of all the machinery that we've already developed, we can state the proof very, very briefly. Okay? Obviously, if you don't know those things, then it takes a while to prove these things. So what is the statement? The statement is, suppose V is a finite dimensional complex vector space. Okay, so let me write this down. Let me make a little bit of space for myself. So, okay, so the statement is, suppose, so this is theorem 6.38, Schur's theorem. Schur's theorem. It says, suppose V is a finite dimensional complex vector space, and T belongs to is a linear operator. Okay? Then V has an upper triangular matrix with respect to an orthonormal basis. Is that okay? which is exactly what I said a minute ago, right? Like, so we already proved that you can do it in the general case with respect to some basis. Then I showed that if you can do it with respect to some basis, you can do it with respect to an orthonormal basis. So you combine them, you get this. Easy peasy. Is that okay? All right. Okay. So yeah, that's basically what the proof is saying. Any questions about the proof of Schur's lemma? Let me dash it. Is it making sense? All right. Okay. So now we look at linear functionals on the inner product spaces. So, okay, so now let's see. So the story says the following. Okay, so let me read the story and then I can summarize it with. So since linear maps into the scalar field play a special role, okay. So linear maps, remember in general, we were saying there are linear maps from V to W, right? Now what we're going to do is we're going to focus on the case where W is just the field F, right? This is fine. This is also a vector space, right? It's a special kind of a vector space. This I already had actually mentioned it when we were doing Hoffman and Kunz, right? So here what we are saying is these have a special name and they're called linear functionals. So if you have a linear transformation, yeah, so let's look at the definition. Okay, so let me write the definition. So definition 6.39 for a linear functional says the following. It's basically so a linear functional, okay, I'm just trying to be a little bit sloppy here. Okay, so let me write it. So when I write Fn is just function, okay, don't get confused. I'm trying to write shorthand. A linear functional on V is a linear map V to F. Okay, so i.e. an element of what? L V to F. Right? Is that okay? Is the definition clear? It's just a linear map where you're restricting to F. That's all. There's nothing very deep here. But it turns out this has like some very, very interesting properties. Okay. And we'll see it goes through all the way. Okay. So there's like some very, very beautiful things that you're about to witness. So please try to follow along. Otherwise, it wouldn't look pretty. It would just look annoying. Okay. So here are a few examples. So the first is, okay, let's try to get some feeling for what linear map is. So suppose the linear function is. So we take this F3, this map from F3 to F defined as follows. So you have Z1, Z2, Z3. Okay, and then this maps you to 2Z1 minus 5Z2 plus Z3. Okay, some combination. Okay. So the right. So here's an interesting observation about this. Okay, so one can write phi Z. Okay, so if I wanted to write it as an inner product with Z, what would I write here? Can I write it as an inner product with something? So my handwriting is really bad. Z2 plus Z3. If I wanted to write phi Z as an inner product of Z with something, what could I write?
You can inner product with the vector with coordinates 2 minus 5.
Do you see that? Does it make sense? So you could take inner product with U, and U could be what? 2 minus 5 and 3. Make sense? You can do that, right? It looks reasonable. So what we'll show is that this is actually true in general. Okay. So here, like it had a very simple form, so you could just read it off. But the statement that we'll show in a moment is that regardless of what linear function you have, you can always do this. Okay. So let's see how this happens. Yeah, so okay, in the assignments, I think this example is a running theme. Okay, so I'm not going to do this example in class, it's in your assignments. Analyzing basically this linear function. Okay? So as we look at all the properties of linear functionals, there's an assignment question, I think in assignment 11, that will ask you to apply those things to this example. So I will not do them in class. Okay? Yeah, I'm sorry, we're just running a little bit short on things. I have to do this, unfortunately, but it'll help you understand, I'm sure. If you have questions, you can always ask. Okay, so now let's understand what is going on. So like I already mentioned, if U is some vector in V, then the map that sends V to VU is obviously a linear functional, right? Because you can check all the linearity properties, okay? So let me write it. So if U is in capital V, then the map v to v comma u linear function. Yeah. Oh no, I forgot to check M. Where is M? Is it making sense? I'm sorry, I forgot to ask. Are you sure? If anything is unclear, you stop me, okay? I completely forgot because yeah, okay, good. So linear function is fine. The previous, what did we, the Schur's theorem was fine, right? You understood the statement. Okay, good. All right. Okay. So now, all right. So the next result shows, right? So like I was saying, okay. So we already know that this map, this inner product, is a linear functional, right? Because you can check the properties. What is the property? That it's sending it's a map, it's a linear transformation from some vector space to a scalar. This is easy to check. Whether it's linear or not, you can check immediately from the properties of inner product, right? Okay. Now what we are saying is that every, and this is like mind blowing. I don't know how to draw the emoji for mind blowing. Let me see. Okay, that's my mind blown emoji. It didn't come out very well. Okay, so what does it say? So it says every linear function on V has this form. Okay. All right. So, okay. So this is actually called formally Riesz's representation theorem. So theorem 6.42, let's make a little space, says the following. So Riesz's representation theorem says the following. So suppose V is finite dimensional and phi is a linear function on V. Okay. Then there is a unique vector. Okay, sometimes this is written as there exists with the exclamation point. Okay, that's the symbol for uniqueness. So there exists, you're familiar with, the exclamation point means it's unique. Okay, it's just saying in case you haven't seen this before. So there exists a unique vector u in V, okay, such that phi of V is the same as V, a product with U, okay, for all V in the vector space. Okay, is the statement clear? I've said it 3 times now, so it should be clear. Okay, all right. But what is your initial? I forgot. I should also write that down. Okay. Is it clear? Fantastic. Okay. So now let's see how to prove this. Okay, so we'll spend a little bit of time on this because this is important. First, what we're going to, so the strategy is, okay, so first we show existence. So first we show existence. Okay, and then in the second step, we'll show uniqueness. So we're going to show that there exists. I mean, everyone is, please, yeah. Okay, so, all right. So first we show that there exists a vector u such that phi v can be written as an inner product between v and v. Okay, so that's the first step. The first step, show there exists a u such that phi v is the same as inner product of v with u. Yeah. So how do we do this? So suppose, so let me make some more space. All right. So let E1 to En be an orthonormal basis. Okay. Then phi v can be written as what? So phi v, what we're going to now do is we're going to write the vector v itself as a linear combination of the orthonormal basis, right, in terms of the composite. That is what we're doing. M. Is it okay? Is it making sense? Okay. So what we are going to do now is we're going to write phi as a linear combination of the orthonormal basis, components of the linear combination. So how do we do this? So if you have a vector V and I want to write it in the orthonormal basis E, how do I write it? So we saw this, right? It was one of the statements. Exactly. So it's V EI sum over L, correct? Okay, so let's do that. So we'll write V. Yeah, let me write it as a sum because I'm a little bit lazy. So V EI. Right, this is what we have. Just a second. Let's move this a little bit. Okay, so we have this. And now what can we do? Okay, so remember phi is linear, right? It's a linear map. So I can pull out the coefficients. Correct? M, is it okay? You can pull out the coefficients, right? So if I pull out the coefficients, I'll get phi acting just on EI, right? And I would have a sum over all else. Is that okay? Sorry, my eye gets a bit messy because the pen has a bit of a photo. Is this statement fine? Is this step okay? Right. Yeah. And now what can we do? Well, we can absorb this coefficient, okay, into the other side. Okay, so what we're going to do is we're going to write it as V phi bar EI. Is that okay? Yeah. It's just from the properties of the inner product. Right? We know that so if you take it from the left, there would be no complex conjugate. If you take it from the right, there would be complex conjugate. Right? So we're just doing this step. So this is what you get. And well, we're done, right? That's what you wanted. You wanted V, an inner product with some vector. Yeah. Is that okay? M. The last step, which step? Tell me. This one? Yeah. So here we're just using the following property. So we are saying, so if you have a, so let's call VW, W alpha is the same as, so alpha is a scalar. I shouldn't actually change scalars like, so let's call it A. Okay, so this is a scalar. So if I wanted to pull it inside, I would get V A bar double. A bar is like a complex conjugate, right? Right? This we proved last time. And what happens if you wanted to absorb it on the other side? So if you wanted to do the other side, you could also say this is equal to AVW. Yeah. Okay, so depending on which side you're doing. So that's all we are doing, nothing very complicated. Okay. So is the existence okay? Okay, it looked like a very non-trivial statement by itself, but just by using very simple properties, we're able to show that such an object exists. Now we want to show uniqueness. Okay, and for uniqueness, what is the usual strategy? We try to assume the contrary, right? We assume that there exists two such vectors, and then we try to show that the only way they can exist is if they are the same. Correct? So let's do that. Let's apply that second strategy. So, okay, so let me move this a little bit to the top. So now we're going to look at the second part, which is uniqueness. So uniqueness says what? So suppose, shoot, I actually didn't complete the full argument. Let me complete the argument here. So using these coefficients, we can, using this as the definition of U, we essentially have the final form, right? So that's all this is saying. It's just writing it properly, that U is just going to be a sum of, I should pull it in. There's one more step, right? It's not a linear combination of such different U's, it's one U, but it's linear, so you can pull it inside. I'm sorry, I missed one step. Right? M, is that okay? Yeah, sorry, I missed one step. And now this entire thing is what we're going to define to be our vector U. Is that okay? M, no, B. Wait, what was yours? I didn't write what is your S? Sounds like none of the letters are working. It's fine? It makes sense? Okay. All. So okay, so now let's look at uniqueness. So for uniqueness, we're going to use this. Like I was saying, the strategy is kind of the usual one. So for contradiction, so we are going to suppose that u1 and u2 are both in the vector space, okay? And they're such that phi of v can be written as the inner product with u1 as well as the inner product with u2, right? Because we want to show uniqueness of u. So we say, okay, suppose there are two u's and they give you the same answer, right? So what can we do with this? Well, then let's take the difference. So if we have v, so phi v minus phi v, this object is 0. Obviously, we're subtracting the same quantity. Okay, so this is from the left hand side. From the right hand side, we will get what? V u1 minus V u2. Is that okay? Yeah, okay. So this is what we're writing. And then we can use linearity again, right? So we can use linearity for the inner product and get this expression. This is fine. Yeah, okay. And what that means is that this property is true for all vectors V in the vector space, right? Is that okay? So what do we want to do now? From this step, we want to somehow conclude that u1 minus u2 has to be the 0 vector, right? Because we want to show that they're identical, right? So you want to show that the difference is with the 0 vector. Is it making sense? S. Okay. So how do we show it's a 0 vector? Any ideas? So you know that it's true for all V's, and we know that W. So if you have two vectors, whose inner product gives you 0 with itself, then that is equivalent to saying that the vector itself is 0. Right? So you use this property and you use this fact. How would you show that u1 minus u2 is 0? Any ideas? Exactly. Okay, so what was the suggestion? Anyone else? Did anyone else think of it? Think of it independently. If you didn't hear, that's fine. So using this step right here, and the fact that it's true for all vectors, and using the fact that inner product with itself becomes 0 only if the vector is 0, we want to conclude that u1 minus u2 is 0, right? Because we want to say that they're the same vector. How would you do it?
The property to use this if we block comma 0, a 0 with the inner product of V and 0 in any form uses 0. But when by here, it would property to use it.
Try to use this. Maybe there's another way to do it, but here's just one line. Yeah, does that make sense? You could choose any V, right? T. It's already clear for you. Okay, fine, no trouble. So we're going to take V to be u1 minus u2. Okay, and then you immediately get it. Reasonable? M? Okay. Okay, so we did this. So basically, what did we do? We showed that there exists a U and we showed that it is unique, both. Okay. So that's like one very, very powerful property that we just proved, this Riesz representation theorem. Okay, just to quickly summarize, the statement was this, that if you have any linear function, right, you can always write it as an inner product with some unique vector. Okay, good. Any questions? Yeah, so note that what we are showing is that for a phi, we can write phi in this form, right? For some, we're basically saying, what are we saying? We're saying phi v can be written as vu. Okay, let me look at the question. The question was, well, we showed uniqueness only for one v, right? Okay, so let's try to understand what we were trying to prove. We were trying to show that suppose I can write phi in two different ways, v comma u1 and v comma u2. Okay, and this u1, the first u1 is such that it holds for all v, right? So the same u1 you can apply on any v you want, whether you take an inner product with u1 or you apply the map phi, it will give you the same answer, right? So that was the first one. The second one is saying the same thing, but it's saying it with respect to u2. It's saying if you take the inner product of any vector v with u2, right, you will get the same answer as if you applied the map phi on v2 or on v, right? Now the point is, if these things are true, okay, we just showed that it would imply that for all vectors, for all v, u1 minus u2 has to be 0. Okay? So one of the consequences of this fact, there can be other consequences. One of the consequences is that u1 minus u2, u1 equals u2. That's one of the consequences. Okay, so it just follows from that. It's not like you're saying that, for each we have to prove no. You've already assumed that u1 and u2 are such that they work for all v's. Okay, and then you're saying if you had such u1s and u2s, then it would have to be the case that u1 minus u2 is 0 as one of the consequences. Okay? It is saying nothing about, like, for instance, let me give you a slightly better example. Maybe if you had u1s that worked on some subset of v's, okay, then we cannot say we cannot guarantee uniqueness. Okay, so if this property, instead of saying it holds for all v, if it held for all v, which is inside some v prime, which is some subset of v, then we don't know if the property is true. Yeah, is that right? Any other questions? Is there a question? Okay. Anything else? Can we move on? We're doing good on time. Nice. All right. So now there is this very nice example in the text. Let me tell you the purpose of this example. Okay, so example 6.44 and example 6.33. What they're doing is they're giving you some kind of an inner product. Some kind of a linear function. So they give some linear function for which it's not obvious at all, what u should be. Okay, that is the whole purpose of the example. So in the first example, we saw it was immediate that you could write it as an inner product with some u. Right? Here, it's deliberately giving you an example where it's not clear at all that you could construct such a u. Okay? And it will tell you, what you could possibly think of as a reasonable option for you, but that doesn't work. And then you have to use the general theory that we just developed, right? Where we said u was a combination of these u phi, u ei, ei, right? Oh, sorry. Okay, and then you can do it. Reasonable? Okay. No, I think I messed up. It's phi. A 5 bar, whatever it does. Is that okay? So you have to actually apply this thing, and then it will be okay. So that's the essence of the example. All right. Can we move on? Is it okay? Things are making sense. Nothing's getting too overwhelming. Are you okay? No? Okay. Yeah. Okay. So let's continue then. So great. Now we're going to make some small remarks about computing u in general, which is what I mentioned. So suppose that, as usual, v is finite. I is a linear function of v. Okay. Then we already said that to finding u, finding a u such that phi v equals pu for all v is simple, right? Because we have an explicit formula. So what is the explicit formula? So u, what did we write u to be? In the previous thing, we wrote it as the sum over I, phi. So if you have some basis here, and then you can write here. It's fine. I just explained this a second ago as well. It's the same thing, okay? I have not said anything new. But here's something interesting that one of you might have asked. It looks like the choice of u depends on the choice of orthonormal basis, right? Which is a bit odd. Right? It shouldn't. The choice, since u is unique, right? It shouldn't depend on your choice, and that is true. It doesn't depend on the choice. Okay, so everything will conspire such that it will be independent because we proved uniqueness. Had we not proved uniqueness, we could not argue this. Okay, making sense? Okay, so that is basically what it's saying. The right-hand side seems to depend on E1 to En, but we showed that there is a unique U. Okay, so therefore basis dependence doesn't matter. So even though U seems to depend on the basis, seems to depend on our choice of orthonormal basis. So you see how the ideas are all coming together, right? Like you have this notion of orthonormal basis, which we're using to sort of write these objects down and so on. It was orthonormal, right? Or was it just any basis? No, it was orthonormal because we use the fact that you can write unit product. Sorry. Because it's crucial that this is an orthonormal basis. So even though it seems like you might depend on the choice of orthonormal basis, because we proved uniqueness, proved U is unique, the choice doesn't matter. It doesn't matter. Any questions? Good. Yeah. All right. Fantastic. Okay. Can we move on? Is it okay with everyone? Oh, all right. Okay. So now, what we'll do is we will look at the definition here and state some useful properties. And we are going to sort of skip. Actually, we're not even going to do this. We've sort of skipped this. I'm just going to tell you one definition, and then we're done with this section. Okay? Because we don't have that much time, unfortunately, but we can at least, you should know the concept. Okay, so the concept is called an orthogonal complement. So definition 6.45 defines something called an orthogonal complement, which we write as U with a verb. Okay. So what this says is the following. So if U is a subset of V, then the orthogonal complement of U, okay, which we denote by U is the set of all vectors in V that are orthogonal, right? That are orthogonal. So this is completely expected. Orthogonal to every vector in U. Okay. A very, very simple definition. It has lots of nice properties which we are not able to prove, but at least you should know the definition. Okay, and then if you're interested, you can sort of continue. And how would you write it formally? So if you had to write it formally as a set, so if you wanted to write it as a set, we would say it's the set of vectors in V such that V comma little u is 0 for all U in capital. And my U's and W's will go. Right? So let's check. Okay, so this is exactly what I wrote. Correct. So it's V in the capital vector space. Sorry, in the capital V vector space, such that the inner product with all vectors of capital U is right. That's what we do. Right. It's correct. Makes sense. Good. Fantastic. So now we can move on to chapter 7. Okay, so we are done with this part. Yay. So now we look at 7a and we'll go at least, we'll try to go as far as 7.10. Okay, that is the plan. If I'm not able to do it, like I said, I'll send you a recording. And please go back and study it because it's going to build on top of each, the previous lectures. So if you don't watch it, it would be hard to follow the next lecture. I think I made that mistake last time, but now we don't have much of an option. That is okay, right? Because I can also switch. I can also just keep teaching without you having to look at any lectures, and then I can give you the recordings later if you fall behind. But that's going to be more burden in the end. But with this, you have to commit to watching the lectures before coming. Because otherwise things are building on top of each other. It'll not make sense if you miss lectures, like miss the recordings. Yeah, okay. So I'll try to do it before like whatever 4 p.m. or something. Is that reasonable enough? Okay. All right. So let's do this. Let's try to finish it anyway, but if you can't, we'll do it. Okay. Right. So now it says the story here is that the deepest results in inner product spaces deal with the subject that we are looking at now, which is operators on inner product spaces. Okay. Sorry, I messed up that sentence while reading it. And these are actually very, very interesting. Okay, so you'll see like they're going to come up with like completely crazy definitions. Okay. And you'll be like, okay, why? It doesn't make any sense. And then you'll see that everything sort of falls in place. Like you have very, very beautiful properties that emerge. And it's going to be like just like in the previous one when we were looking at these linear functionals, right? The notion of orthonormal vectors is very, very useful, right? To be able to show these things. So we're going to build on top of the previous structures. Okay, so that's one. And by using properties of the adjoint, we develop a detailed description of several important classes of operators on inner product spaces. Okay, so adjoint we're going to define in just a moment. Okay, and using these, we'll try to classify what kind of operators exist and so on. Okay? And what is the definition of an operator compared to a map? So operator goes from V to V. Right? Maps can go from V to W. Okay? So that's why he's harping on about operators. That's kind of the point. Okay, great. So what is the new assumption in this chapter? So here V and W are going to denote finite dimensional inner product spaces over F. So okay, so let's start then. So now we look at self-adjoint and normal operators. So this we'll probably do next lecture. So this lecture we're going to focus on self-adjoint. So we have to define what the word adjoint means first. Okay, so here is a very weird looking definition, okay, which a priori it's not clear why it's a good definition, but let's write it down. So definition 7.2 says, so it's the definition of an adjoint, T star. So it says suppose that T belongs to the set of linear operators from, linear maps. Okay, I keep saying linear operators, so forgive me, okay, I'm messing up the notation. Linear maps from V to W. Okay? The adjoint of T. Okay, so this is a new object, a brand new object we're defining, is the function T star. Okay, it is some new object, so we're just calling it T star, which goes from W to V. Okay, so T was going from V to W, T star is going to go from V to W to V. And the definition is as follows. The requirement is as follows. If I take T applied on some vector V, and take an inner product with some vector W. If I do this, then the result should match exactly the following. So you take an inner product with V and T star applied on W. Okay? So it's a very strange definition, right? Like we're defining it by saying that it's not even clear such an operator exists. Right? We're just asserting, okay, like imagine there is some operator that does this. Okay, now let's try to see why this definition actually makes sense in view of what we just learned, in particular, in view of Riesz representation. So, okay, so let's see. Right. So that's exactly the question. Why? Right? Why does this definition make sense? So, okay. So, oh, I forgot to mention this is true for all V and W. So V in capital V and W in capital. Okay, so this property needs to be satisfied for all vectors in both vector spaces. Okay, any questions about the definition itself? Is it reasonable? The definition makes sense? Yeah. Okay. Right. So why this definition? Let's try to understand that. So what we're going to do is we're going to fix. So we fix W in capital W. Okay. And we're going to consider the linear functional on V that maps the vector V to the vector TVW. Okay. So we're just going to consider the function, right? It is a function. Is that okay? Right? It's just an inner product. It satisfies the properties. Okay. Now, note the first thing to note is that this map depends on what? So what are the things that this map depends on? Okay, it's a linear functional on V. So what does this map depend on? Right? What does the map depend on? So I'm saying, consider this map which maps, V to TV comma W. So what does the map depend on?
Yeah.
T and W, right? Is that okay? Okay, so that is fine. Now, what we're going to do is, because it's a linear map, using Riesz representation or representation, I always say it the wrong way. So using Riesz representation, we have that there exists a unique vector. So there exists a unique vector. I'll use that notation, okay, just to be a little bit compact. So there exists a unique vector, let's call it U, in capital V, such that TV comma W is the same as V in a product with U. Is that okay? And remember, what does U depend on? What will U depend on? T and W, right? Those are the parameters. M, are you with me? Did you fall behind? Yeah, okay. So what we're doing now is we're saying, right, look, so here we have a linear transformation, a linear functional, right? So it's a linear transformation that maps something to a scalar. So we have this, and Riesz's representation theorem said what? It said that if you have any linear transformation phi, right, for this one can find a unique vector. So for all five, linear transformations phi, there exists a unique vector U such that phi of V is the same as V comma U. Okay, so we're using that fact now. We are saying using Riesz's representation for this map. Okay, it's a linear function. So this map, let's call it phi. Okay. So under phi, the vector V is mapped as shown. So phi V is the same as TV comma W. Right? Okay, so this is the map. Now for this map, what I'm saying is that you can write, so I can write phi V, right, equals V comma U, right? And what was phi V? Phi V was TV comma W. Right? And also note that this phi, like we argued, this phi depends on what? It depends on T and W, right? So I'm adding the subscript to show the dependence. So phi depends on T and W. When you apply V, you will get TV comma W, right? So the vector U will also depend on T and W because it depends on the map. This is making sense. So if I give you a map, you can find the corresponding vector. So whatever the map depends on, the vector will also depend on that. Not saying anything very deep, right? So this vector U is going to depend on TW. Okay. All right. So let's see what else it says. It says let us call this unique vector T star W. Okay. So what I was calling U TW, it's saying let's call this vector. So let us call U TW. Let's define it to be T star W. Some notation. Okay. And why can I do this? Because Well, starting with W, T can map. Like there is a linear transformation that would map it to whatever vector you wanted to map it. Correct? You can do that. That is not a problem. Okay. So T star W is the unique vector in V such that TV equals V T star W. Okay, so it's all hinging on the fact that there existed some U. And because there is some U, you can write it as T star. Okay, this is why the definition makes sense. Okay, it's a very sort of like it's a distillation of ideas from a long, long time. So that's why it looks very dense to us, but it turns out to be very useful. Okay, any questions about the definition and why it makes sense? Yeah, maybe I put the whole thing. Is it too small? Maybe it's too small. But questions? Is it okay? You'll have to speak louder. Yeah, okay. So let's do it one more time. Okay, so let's go through the argument. What we were saying was, if you have a so what is the definition of adjoint? Okay, so adjoint was given a linear operator. So given a linear operator T, right? The adjoint of T was defined to be this map T star, where you're mapping, where you're requiring that the action of T on V in a product with W matches exactly the inner product of V with some new operator acting on W. Okay. So that's the definition. Okay. Now it's not clear that such an operator would exist at all. Okay. That part is not clear. So now what we're doing is we're trying to justify why this definition sort of makes sense. And the way we are doing it is we are saying that it is a linear functional, right? So it is a linear functional that is taking you from, right? So it's taking, so there's some linear functions which is taking a vector V and giving you TV comma W. Right? So we can treat it like this. And this linear transformation depends on T and it depends on the vector W. Correct? Okay. Now what we want to argue is that so we're going to use the Riesz representation theorem, right? So what does the representation theorem tell us? It tells us that there exists a unique U, which will also depend on T and W, right? Obviously, such that phi TW of V would be the same as TV comma W. Correct? And phi TV of that's already the definition. This would be equal to V comma UTW. Right? Now, what they're saying is that because this vector is unique, one can just call this vector T star W. Okay. And the uniqueness and all of those things would just follow because it's an inner product structure. So everything sort of checks out. Okay, so you can just restrict to basis, actions on the basis, and then from the basis, you can map basis to basis, and so you'll be able to map for every W, you would be able to find. So you can map every basis element in W to whatever this object is. Okay, and then use that to define T star completely. Because this was true for all W, right? All I'm saying is you can restrict to the basis of W and use that to define the map T star. We know that, okay, to specify a linear operator, it's enough to define its action on the basis, right? That is all I'm saying. Because this was true for all W, I was saying you can, if you wanted to do it, you could just pick some basis in capital W and see how, which vector you have to map it to using this. Because for each basis element, you would have a unique vector to which it maps, and everything else will follow by linearity. This will make sense. Okay. The only non-trivial thing here is that there is this W sitting here. So the W is introducing different vectors. In Riesz's representation, there was just one vector. So for every W, there is a unique vector. So you look at the basis elements, find the unique vectors, and then T is the transfer. T star would give you the translation. Is that okay? Making sense? All right. Very good. So we've understood the definition. We've understood why the definition makes sense. Can we move on? Okay. Right. So now let's look at as usual. Let's look at a very a quick example. To push this side a little bit. All right. So this example is basically saying the following. So you suppose, okay, so this is example 7.3. We're doing reasonable on time, actually. I think we have another half an hour to be able to. So until when what were we supposed to cover? Do you remember? 7.10. Okay. Let's see. It's okay. I'll send you a recording. I think it's better to go slow and then give you a recording than to rush, because then nobody understands, right? So I think that would make much more sense. Okay. So So we have t going from R3 to R2. Okay. And t of x1, x2, x3 is going to be just a linear functional, right? So they're defining it in whichever way they want. So this is 3x3. Oh, sorry, it's not a linear function. I'm sorry, it's a linear operator, right? And then we try to find the adjoint of this operator. Okay, so it's giving you as an example, it's considering some linear operator. So this is the operator. Now it's basically going to show you how do you find it. So the question is find t star. Okay. Yeah, linear transformation. Sorry. Yeah, you're right. I'm sorry. I always say operator. Yeah, just know from the domain and region. And thank you for correcting me. It's a linear map. So it's a linear map, right? And we want to understand what is the adjoint of this map. So how do we do it? So let's follow the examples. It says, so here, t star would be from what to what? So if t is going from R3 to R2, t star would go from, it flips, right? R2 to R3, right? Okay. So, right. So now if you want to compute t star, okay, he's just giving you one way of doing it. Okay? There are many ways of doing it, obviously, as you're well aware. So you think to compute t star, let's just fix some y1, y2 in R2. Okay. And then we try to see what the action of this is. So, all right. So what is the definition of t star? We know that it has to satisfy for all x1, x2, x3, and y1, y2, y3 the following equation, right? Y1, y2. Sorry, it has to satisfy what? It has to satisfy the linear transformation acting on x1, x2, x3, right? And y1, y2 stays the same. Correct. This is where the definition of what t star means. Correct. Okay, so if you do the computation, I'm not going to do the computation, I'm going to skip a few steps here. So when you do the computation, you're going to get some expressions. You'll get x1, so you'll get x2, y1 plus 3x3, y1 plus 2x1, y2. Okay, so there's some computation you do. Now, what is very nice here is you can pull them into separate parts. So you can write it as an inner product between x's and y's, right? So let's do that. Let's write it as an inner product, x1, x2, x3. And then we have 2y2, y1, 3y. So far, so good. Is it making sense? Okay, we didn't do anything. We started with what the definition of t star is, and we said we'll apply it to some arbitrary y1, y2, right, to see what happens. And what we got in the end is inner product of x with some different y's. Right? That's fine. Okay. So what does that tell you? That tells you that the action of t star, okay, on y1, y2 is essentially what? So the action of t star on these vectors is supposed to give you this vector, right? You see what happened here? I don't know. My handwriting is so bad, I can't even tell what I wrote. Y1, 3y. Is this okay? Yeah, so here we did it explicitly. Because, not explicitly, sorry. Here we did it because we could kind of see the form very clearly. If you could not split it like this so easily, like suppose you got some expression here which was not so easy to split, then it might get a bit more involved. So then you may have to use the more general definition of finding files and so on. Right, like what we discussed here, no? So for you can apply the Riesz representation theorem for every TW. You will find this UTW vector. So then you'll have to do it through the UTW vector in the general case. Okay, so here, because we managed to find a very nice form, we could simplify. Is that okay? Making sense? Okay, fantastic. All right. So there is this other example. Can you guys do it as homework? It's probably not in the assignment, but here, fine, let's just do it. I'll not write it, okay? I'll do this one quickly. So suppose u and x are vectors in V and W. You define a linear operator T by the following. Yeah, so it basically takes the inner product with some fixed vector u and multiplies it with some fixed vector x. Okay, so TV is the same as VU acting on x. Okay, and we are supposed to find what T star is. Okay, same idea. You start with V T star W, write it as TVW, expand it out, and somehow get V on one side and the remaining thing on the other side. Okay, and that will give you how T star W is. Is that okay? All right. Okay. So in the two examples above, T star turned out not to be just a function, right? But it is also a linear map, right? So in this example, you see this is a linear map. Yeah. And this is also a linear map, right? You're sending a bunch of vectors and you're moving the coordinates around. So it satisfies all the linearity properties, right? So now what we are going to figure out is slowly we are going to build, we're going to understand what are the properties of the adjoint. Okay, so first there was like a very strange definition. We looked at how to use the definition and extract what the adjoint is. And now we are making observation about the properties that the adjoint has. Because the first observation we made was that in both these examples, right, the adjoint turns out to be linear. Okay, so as mathematicians, we want to understand, is this true in general? Right? Like how general is this result? Is it a fluke or is it something that happens in general? Turns out it happens in general. Okay. And the proofs in the next two results use a common technique. What we're going to do is we're going to move T star from one side of the inner product to the other side. So that is just the high level idea of the proofs involving adjoints. Okay? So let's do that. Yeah, I know you guys, it's a long lecture. I don't know. 1.5 hours is too long, I agree. I think we should just have a 1 hour slot and then give you some break, and even then you're struggling to finish. Okay. Yeah, sorry. Okay, so let's state the theorem, right? So let's state the statement, the theorem statement more clearly. It says the adjoint is a linear map. Okay, so if T is a linear map from V to W, then T star is also a linear map from W to A. Here's the okay, so how do you prove this? The proof is actually surprisingly straightforward. So let's do this. So the proof says the following. The proof proceeds as follows. Well, first of all, the statement is clear for the theorem. Yeah. K, was it K? No, T. Oh. Is the statement clear? Okay, good. Your T, right? No. Your T? Okay. Yeah, sorry, I know it's hard to recognize by initials, but limitations. Okay, so now we suppose that suppose T belongs to is a linear operator. T is a linear operator from V to W. Okay, and we're going to fix two vectors in W. Okay, so you take any linear operator that is going from V to W, you fix two vectors, W1 and W2, in the codomain. Okay. Now, for V in capital V, it holds that V T star W1 plus W2. Okay. This is going to be the same as what? What is the definition of the adjoint? Yeah, so it's TV W1 plus W2. Is that okay? And what do we want to show? Okay, so we have to remember what we want to show. We want to show that V star is linear. right? So that is why we started with two vectors in W, because T star acts on W. Okay, so we want to show that it acts on W1 plus W2, just the same way as it would act on W1 plus the way it would act on W2, right? That's what linearity is. So let's expand this. So you'll have TVW1 plus TVW2 because of the linearity of the inner product, right? This we can write as V T star W1 plus V T star W2. Why can we do that? M, why can we do this? Yeah. So here we're using the definition of adjoint. Okay, it's a little bit different from doing it with the complex numbers. Okay, so here we're doing it for operators. So we're using the definition of the adjoint to do this. Yeah. So this is fine. And now what do we have? Now we can use the linearity of the inner product, right? To do what? To say that this is V T star W1 plus T star W2. Right? Is that okay? So what does this show? It shows that, this action. So the action here is the same as this action. Right? So therefore we get, and also note that this is true because it holds for all V's. Okay. So it is the same idea. You take the difference and then you can take V to that vector, and then therefore they have to be equal. Okay. Don't do it arbitrarily. There is a reason. You can conclude from, okay, so what I'm saying is from this statement, to be able to conclude the statement below, you have to use the fact that this statement holds for all V. Okay, and it's related to the point you were asking, right? So because it holds for all V, therefore, when you take the difference, you can take the vector to be the difference vector, and that would mean that the thing has to be 0. That is how you get the equality. Okay, and it's going to use this repeatedly. Although the text doesn't say it explicitly, it's sort of understood. Okay. Any questions? Good. All right. So we proved one part, which is that the vectors are linear. Sorry, if you take linear combinations, so we showed this. So if you take linear combinations, then you would get the thing acting, the linear combination of the things. Right? Is that okay? One can do something very similar for the scale. Okay, so this part of the proof I'm going to leave as homework for you. Okay, because we have to show two things. So in Hoffman and Kunz, we used to do the following. We would say alpha plus C beta, right, directly. Where C used to be the scalar. Here, what we're doing is we're doing alpha plus beta first, and then we're doing C separately. Making sense? Okay, so the C part is here. So I'm going to leave it as homework. It's very straightforward. You can check. Okay. So at the end of it, this means that T star is a linear, as we wanted. So now we look at a few properties of the adjoint. So here's the first property of the adjoint. Yeah, let me state them and prove them directly. I think it would be much faster. So let me do the first, the third, and the last. Okay. And these two I will leave as homework, unfortunately, because we're running out of time. Okay, but the proof is very straightforward. The notes are already online. You can check. Yep. So let's do the proof of the first one. The first one is saying that now if you take linear combinations of operators themselves, okay, what can we say about the adjoint? Okay, note what we're doing here. The definition of adjoint itself was so crazy, right? But not only could we figure out how to compute the adjoint, we could figure out that it's a linear map. And now we are saying how to compute the adjoint of linear combinations of linear operators. Okay? So how do we do this? We compute S star and T star. How do we compute S star and how do we show that the adjoint of S and T is the same as the adjoint of S plus the adjoint of T? How do we show this? So let's do that. Let's start with the definition as usual. So we're going to start with V. So V and W are always going to be, so V is going to be in capital V and W is going to be in capital W. Yeah. So let's write it down. So S plus T star acting on W, right? And is it making sense? Yeah, let me know, okay, if you fall behind, because sometimes I forget to check. Just yeah. This is for everyone, of course. Right, so what is the definition of the adjoint? that we can write it as S plus T acting on V with W. Is this fine? Yeah. S, you'll fall behind here. Sorry, I know it's tiring, but we have to do this. Okay. So right. So the next step is we're going to use linearity of S plus T, right? This is fine. So SVW plus TVW. Right? Is okay? This is just from the definition of what S plus T means. There's nothing very deep happening. Now what are we going to do? We're going to do the same thing. We're going to move T to the other side using the definition of the adjoint. So what are we going to get? We're going to get V S star W plus V T star W. Correct? M R S. S got lost. Where did he get lost? This step? This one? Did I mess up? Which step should be W? Let me write down the steps so that you can tell me 1, 2, 3, 4. Which one are you talking about? Okay. Okay, so far it's okay with everyone? I have not messed up, right? It seems correct, yeah? Okay. Got it? And now we can use the linearity again of the inner product, right? So you'll get SW plus T star W. Correct? Yeah, reasonable. And then again, the same trick. This object has to match this object. Why? Because the statement holds for all. So, T. Was it T? M? Is it okay? All right, good. So this is exactly what we are decided. So point 2, I'll just state, I'll not look at I'll leave the proof to you. So lambda T star is the same as lambda bar T star. Okay, so it's actually behaving like complex conjugation a little bit, right? You can already see that. So lambda T star is the same as lambda bar T star. Okay. The proof is very, very similar. You're just going to move things around. Now this one is kind of nice. Here it's saying what happens if you take the adjoint twice? Okay, so if you take the complex conjugate twice, we know you get the same thing back. Is it something similar here? It turns out yes. So how do we show this? So again, we're going to do the same trick. So we're going to start with W, T star star V. We're going to write it as T star W V. And this would be what? Okay, so now here's the things are a little bit different. Now we're going to write the complex conjugate of this expression. Okay, the first step is from the definition of adjoint, correct? Yeah, so the definition of adjoint was what? That's fine, right? For everyone. Okay, good. So in the next step, what we're going to do is we're going to take the complex conjugate of this object. So we're going to write complex conjugate of V star, V comma T star W. This is fine because we had A, B. Yeah, we should write VW, say for example. The complex conjugate of this thing is WV. Right? This we already did. So we're just doing that. And now we're going to apply the definition of adjoint again. Okay, so definition of adjoint again. And this would give us TV acting on W, but it's still under the bar. Okay, so we applied the definition of adjoint of the expression under the bar. M. Is it making sense? Yeah? Okay. So this is what we get. And now, okay, now you can apply the definition of complex conjugate again. What would that give you? W comma TV. Correct? Okay, and magic. Yeah? We got this again, right? T star, we back to T. Yeah? Good now? Okay, nice. So the C part is done. D part is identity, so this is completely trivial. You'll check for yourself. This is homework. The last part as well, we can quickly try to do. So the last part is now, so we saw how the sum works. Now we're going to see how the product works. Right? These things are sort of useful. So let's see. So ST, if you want to construct the adjoint of this, it is asserted is the same as T star S star. How do you do this? So again, the same trick. So you start with V ST whole star acting on U. Correct? Now, what is the definition of the adjoint? It's ST acting on V, U. Correct? And now Now we can apply the definition of the adjoint, but only on this part, only on S. I can do that, right? There's no reason why I cannot. So I'll have TV, and then I'll have S star U, and then I can apply the definition again, and I'll have V, T star S star U. Okay. And now what do we have again? We have V on the left hand side as before, and the other thing is what about it? Making sense. Yeah. And we are again using the property that you had mentioned, that it has to hold for all V, otherwise it doesn't work. Yeah. So this is how you conclude. Okay, fantastic. So we managed to finish that.
S and D are they work on different in that much, like they work on different some points. And if this the thing you're satisfied is
it will. You can check it at home. Yeah. There's no funny business happening here because every in these maps, right, they're going from like S and T, like the domains and ranges are defined such that S and T compose properly. And then you're just moving things around one by one. It will work out. You can double check. Yeah, that's a good point. Okay, so the question he was asking was, these are not operators, right? These are maps. So I have to be careful about the domains and the ranges, right? So this is going from V to W, domain and codomain, right? And this one is going from W to U, and I'm mixing all of them up. Are things consistent? He was worried, which is good. You should worry about this, and you can check. It'll work out. Okay. Any other questions? Shall we continue? Fantastic. So this next result is, this is entirely. This is 7.7. We can skip this. It's a beautiful thing if you have the time. This is like, if you want to have extra joy in life, you can read it. It's really nice, but we don't have as much time. Okay. All right. So moving on, we define the notion of conjugate transpose. Okay. So far we defined the notion of an adjoint. Okay? Conjugate transpose sounds like a matrix operation, right? So you take the transpose of a matrix and then you do some complex conjugate. It turns out that these two notions are very closely related. So the notion of an adjoint, so adjoints, and the notion of a conjugate transpose are very closely related. Okay, and so we'll try to see what that is. So first of all, the definition of conjugate transpose. So definition 7.8 says conjugate transpose. Okay, and it's exactly as the word says. Okay, so first apply transpose. Okay, so it's for a matrix. Okay, so I'm going a little bit fast now, but you understand. Okay, so given a matrix, we first transpose the matrix. That is the first step. Okay, and the second step is you take entry-wise complex conjugate. Okay, is the definition of conjugate transpose clear? Yeah. Okay, so that is all it is saying. Here is just an example. Okay, so you have a matrix, you take the transpose, and then you take complex conjugate element terms. Okay, it's just clarifying the definition. Nothing anything. Yeah. Okay, good. All right. This is just a small remark saying if you're in the reals, then of course this conjugate transpose is just transpose. Conjugation doesn't change anything, right? So that's completely trivial. So this can remove. Okay. The next result, and this is like sort of, we reached 7.10 in the last 5 minutes. At least we can state it. Okay. If I'm not able to do the proof, I'll give you a recording. So the following result shows how you compute T star given its matrix. Given the matrix of T, how do you construct the matrix of T star? That is what we're going to do. Okay. So given the matrix of T, constructing matrix of T star. Okay. Because so far we did it very abstractly, right? He said, oh, there's some linear operator, yada yada, and then now like, imagine you're given a matrix, how would you do? Okay. So here's a very, very cool statement. It's also kind of nice. So let's understand the statement properly. So this is theorem 7.10. Okay. So matrix of T star. Okay. So first note that T star is well defined by itself. Right? It's a well-defined operator. We can ask what is the matrix representation of this T star. Okay. And what we will find is that when you construct the matrix representation of T star, it would turn out to be exactly the complex conjugate of the matrix for T. That is completely wild. Why? Like it's like a priori, you have no reason to believe that it would have such a clean correlation, right? So that's the statement. So what is the statement? So it says let T be some linear transformation from V to W. And suppose that E1 to En is an orthonormal basis, okay, of V. And suppose F1 to Fm is an orthonormal basis of W. Right? My W has too many wiggles. Okay, this is fine. It's just defining the basis. Then the matrix element, okay, this is like a slightly different notation to what we were using in Hoffman and Combs, but the idea is the same. So the matrix representation of T star relative to F1, Fn, and E1, En, okay, is the conjugate transpose of the matrix representation of T, E1, En, and F1, Fp. Okay. Is the statement clear? We have 3 minutes. Let's try it. Let's be ambitious. Okay. If you can't do it, I'll anyway send you a recording. Okay, don't worry about it. I'll send the recording, but let's hope you get something out of this. Okay, so how are we going to prove this? So we write, okay, let's do this. So we are going to write MT and MT star, okay, instead of the full expressions, first of all, just as a simplification. Okay, all right. Now recall this very simple fact that when you're writing MT, right, the kth column of MT is basically just the exactly. So it's just the scalars in the yeah, these are just the scalars in the linear combination of T, EIK in terms of F1 to F whatever. Right? So what is it saying? It's saying something very simple. Okay, it's nothing complicated. You take T, apply it on the orthonormal basis. It will give you an answer which would be expressed again as a linear combination of the orthonormal basis of the other scores. Correct? So these coefficients basically form the column of the matrix. It is just asking you to recall this. Is that okay? Yeah? Okay, so that is all it is saying. So it is saying if you write TEK explicitly like this, okay? Yeah, because we don't have time, let me just do it on the thing. Okay, let me not write it again. So if you write TEK like this, right, these objects over here are going to be the column entries for the kth column. It basically is the kth column. Is that okay? Good. All right. And that is almost it. Okay, that is essentially all you need to observe. Why? Okay. So note that the jth entry, the jth row and the kth column would be what? It would just be TEK, FJ, right? Because I already said these are the columns and you're looking at the jth row. Okay. So this is the jth row, kth column. Now here's the fun part. Thanks to all the inner product structure and magic, what you're going to do is you're going to replace T with T star. Okay, so you're going to replace T with T star. And you're going to swap E and F around. You'll make F and E, right? Because it's going from the other direction. And when you write down the jth row and kth column of MT star would turn out to be T star FK EJ. Yeah. All you did was you applied the same argument, but for T star. T star goes from what? Instead of going from E to F, it goes from F to E. Okay. And then what was forming? K was forming the column, right? So K was the index K was on E. Now the index K is on F. Okay. The index J was on F. Index J is on E. Okay. So you can see what is this? It looks like a transpose, but with the flip and the thingies, right? So you get the complex multiplication. Okay. That is the thing. Sorry, I ended up taking a minute longer. I got excited. Very sorry. But that's the proof. Okay, you can go back and take a look. But I think we managed.